you tell us about zeta functions of cubic surfaces, about which you already know something from Alexander's function?
Okay. Well, as our previous speaker, today I will speak about cubic surfaces, and the next day I will speak about other Delpech surfaces. Well, what is zeta function? We consider algebraic variety over finite field FQ. Then we can count number of points. By ND, we denote the number of points over extension of this finite field of FQD. We can write the following. That function of x, it's exponent of this sum. So actually, we need zeta function to count the number of points over variety and over extension of its ground field. Well, for cubic surfaces, we have the following. Zeta function is equals to 1 by where P of t is determinant of 1 means qt by Frobenius element in the following lattice. So what is this? We consider Picard lattice of our cubic surface, and we have the action of Frobenius element on this lattice. So yes, it's vector space since it's multiplied by q. So we can consider a matrix, which is written here, and give it determinant.
Should be peak of the base change, right? Should be the geometric Picard, not just peak of x, but peak of x and q bar.
Yes, of course. Q square here? Yes? Yes? Sorry. Sorry. So actually to find zeta functions, it's the same that find the action of the Frobenius element on the Picard lattice. So it's the same that cyclic subgroups of the while group. Yes? What do we have is this exertion? So what do I want? I want to construct for given cyclic subgroup, I want to construct a cubic surfaces such that the Galois group acts on the image of the Galois groups in the while group of E6 is this one, this concrete one. What do we have for cubic surfaces? For cubic surfaces, what? Yes. I have while group, yes. I have Galois group of algebraic closure, yes. And so here I have a map from here to here. And gamma will be image.
This map was discussed in the previous talk.
Yes, it was discussed in previous talk. So gamma the image of the Galois group, and if I know this image, then I automatically know the zeta function, since we have this equation. So what I want to do, I want to construct for any cyclic subgroup of the Galois group, I want to construct corresponding cubic surfaces with some mild conditions on this. Well, what we have in geometric case, for example. In geometric case, we can't construct any cyclic subgroup, since if we consider a subgroup of while group E6, which permutes exceptional divisor first and 2, and don't permute other exceptional divisors. We can blow down 6 exceptional divisors E1 to E6 and have. Yes, I will use capital letters instead of small. Okay, so E1 E6, then what do I have? The last device will be E6, yes, as the lattice. So some confusion, but not more. Well, I can blow down 6 devices, and I will have a project plane with 4 fixed points, which corresponds to E3 to E6, and 2 points which are permuted. But if I have geometric automorphism of projective plane which fixed 4 points not lying on a line, then it's trivial. So it can't permute to other points. So in geometric situation, I can't have any group, any cyclic subgroup in the while group. What about arithmetic? Geometric automorphism. So I can't realize any cyclic subgroup of this one as geometric automorphism of cubic surfaces. But actually, the good thing that in the arithmetic case, I can do it.
Okay, so could you write down the statement?
I will write down it soon. Well, so.
Actually, a good point to stress why you are analyzing on the cyclic groups.
Or on the cyclic group, since it's an image of the Galois group, and for the finite field, it's always cyclic, of course. Well, what about cyclic subgroups? There are 25 possibilities. And we have 2 principal different cases. Case is that invariant Pecan number.
25 possibilities for conjugacy classes in this while group.
Yes, 25 possibilities for conjugacy classes of elements. How do I see it? It's hard work. You know that order of while group E6 is something like 51,000. Yes. So it's hard work to see these 25 classes, but we can say something about many of it. So we consider invariant Pecan number of X, which is the same that two principal differences. First one, that invariant Pecan number is more than 1. And the second one is that invariant Pecan number equals 1. Here we have 20 possibilities, but it's not problem, since if we have invariant Pecan number greater than 1, then our cubic surface is not minimal. So we can blow down some exceptional divisors and have a Del-Pezzo surface of greater degree. For this surface, we just want to construct such a surface and then blow up some points in configuration of what we want in this case. So here is question to construct the Del-Pezzo surface of a higher degree and then blow up some points. We can do it in any case. For example, assume that we have trivial action of our Galois group. In this case, we need to blow up project plane at 6 points which are defined over our ground fields. But, for example, for F3, let's start blow up points. First 4 points. This is P2 over F3. Something like that, yes? We can choose 4 points. Yes, I will write down the state when I go to this case. Yes. So we can blow up 4 points on projective plane, but when we do it, then lines passing through this point, something like, well, I can't draw it all. But the problem then, after we blow up 4 points on a projective plane of a field of 3 elements, all points on the considered path surface of degree 5 will lie on -1 curves. So we can blow up the 5th point and 6th points. So we can't realize this possibility for all finite fields, but after, if Q is not arbitrary, but not very small, we can do it. Just construct the path surface of higher degree and then blow up some points. I think the path surface of higher degree with the given Galois action I construct tomorrow. But what is this case? In this case, we have only 5 possibilities. And now I write down the statement, as Sergey wants, from the beginning of this talk. The statement is the following. I can write down is at stable. This type of group, this order, and here restriction on fields.
Also, it may be a good point to stress that you have this equality rho equal 1 even before you have any geometrical surface x, yes?
Yes, even before.
It's also a condition only telling you only something about the lattice and the group action on the lattice.
Yes, yes, of course. Well, what do I have? 5 possibilities. It's from classification of Swinnerton-Dyer numbers: C11, C12, C14, C13, and C10. Well, order of these groups will be 3, 6, 9, 12, and 1 more 6. And restrictions will be the following. Here, in 4 cases, we say that Q is odd. Restriction on Q, on field.
Actually,
So,
I think it's the main theorem.
yes, it's the theorem that will. That in these cases exist corresponding cubic surfaces. And here will be restriction that Q is equal to 3K plus 1 and maybe Q odd 2. Well, let's start.
And the other way around?
Are
these sufficient or necessary?
It's sufficient, not necessary. I don't know what will be if Q is even. So for characteristic 2, I don't know the answer.
So the theorem is if the order is like that.
Yes, if the Q is like then so such group can be realized at the Galois group action of some cubic surface. Well, let's start. At first, we can look at this table and understand nothing, since we don't know which this group and what.
And you don't assume that Q is also sufficiently large.
No, I don't assume that Q is sufficiently large. No. So, first we should understand which are the groups, these groups. So consider the group, the while group W is 6. Yes, its order is 51,840. That's the same that 2 in the 7th, 3 in the 4th, and 5. I think it's the third time when this comes rise up on this blackboard. What do we have? We have 27 lines on cubic surfaces. These lines are following. EY, it's exceptional divisors, 6 times. Then LIJ, it's line passing through the pair of points of blow up. 15 number of these lines. And the last is quadric, not passing through the one of point of blow up. Yes. In the while group, we have obvious subgroup, S6, which acts just by permuting these indices. So it's very good subgroup, and we can say very more. Look at this. At first, let's look on elements of order 5. All elements of order 5 are conjugate in this group, since bisexuality theorem. So any element of order 5 is conjugate just to permutation 1, 2, 3, 4, 5, cyclic permutation. But for this permutation, we have two invariant lines. It's E6 and Q6, invariant line. So if any cyclic group contains this element, then this pair are invariant under the action of cyclic group containing this element. That means that if cyclic group contains an element of order 5, then we can blow down this pair of lines. So for cyclic group which acts minimally, its order cannot be divided by 5. It's just 2 and 3. Well, what about elements of order 3? To classify elements of order 3, we want to find a silent subgroup of our while group. Its order is 81, and we can find such a group. Let's consider Fermat cubic over complex numbers. So you see, we classify arithmetic subgroups in group for cubic surface of a finite field, and to do it, I consider a cubic surface geometrical action over complex number. We have geometric action of group of order 81 here. This group is generated by multiplication of variables by the third root of omega over 1. Omega is the third root during this talk. Well, we can map x, y, z, t to omega alpha x, omega beta y, omega gamma z, t. And one more transformation of order 3. It's just permutation of 3 variables. So this transformation generates the group of order 81, which is something like cyclic group of order 3 cubed semi-direct product by cyclic group of order 3. Well, also looking at this cubic, we can see now actions and types of action for any element of order 3. There are 3 types. Type 1 is action which is generated just by multiplication over omega. The one variable, type 2, it's multiplication by roots, by the same root. Two variables, and type 3 is multiplication of two variables by two different cube root of 1. Well, one can ask about this permutation, but it's conjugate to type 3. Well, also, we can see automorphism of order 9 too here. Automorphism of order 9 is generated by cyclic permutation with multiplication by the omega. Well, let's look on this automorphism. What do we have? Consider the first one. The first one, automorphism, let G be the generator. And consider a quotient for surface. So, x by G. It will be projective plane. Why? Since its element have a curve of fixed point t equal to 0. And so we can write down the Hurwitz formula and have the following, that kx by G squared is equal to 3kx squared by 3. And so it's 9. And moreover, it's not singular since we don't have isolated fixed point in this case. What does it mean? That means that for this group, invariant Picard number is equal to 1. So, if we have this group or bigger cyclic group which contains this one as subgroup, then automatically we have that invariant Picard number is equal to 1. And this corresponds to cases C11, C12, C14, and C13. In all these cases, there is a subgroup of order 3 which is generated by element of type 1. What will be for type 2? Element of type 2? Yes, we see. We now have two other conjugacy class in the while group, and also in the while group we know two conjugacy class of element of order 3. These conjugacy classes are 1, 2, 3 permutation and 1, 2, 3, 4, 5, 6. Obviously, for these cyclic subgroups, the corresponding surface is not minimal, since we can blow down exceptional divisors from A1 to A6. So it's not of type 1. And also we can see that for this action, the group doesn't have invariant lines on cubic surfaces. And for this action, it has invariant lines. And in this situation, we have invariant line. For example, x equals to minus y. So, actually, this action is type 2, and this action is type 3. Since they are not conjugate between themselves, they are not conjugate to type 1, and we have only two possibilities, this and this. What can we say in each of these cases? In case 2, we have 9 fixed lines. Not fixed, but invariant. E4, E5, E6, L45, L46, L56, and Q4, Q5, Q6. But let us assume that some group contains an element of type 2 and acts minimally. Then its order will be 2 in k's power by 3. Since it not contains elements of order 9, it not contains element of order 5 since it will be non-minimal, and its order will be so. But if we have the action of group of order 2 in the case power, then one of these curves will be invariant under this action, since 9 is odd number. So in case 2, it's never minimal. And what about the third case? As we see from table, it can be minimal. Let's look. For this action of type 3, we have 6 orbits consisting of 3 disjoint -1 curves. It's E1, E2, E3, then L1, 2, 1, 3, 3, etc. Let's look how curves from this orbit intersect with other curves from this orbit. You see that for each curve from this orbit, each curve intersects each curve from this orbit, yes? And the same for these two orbits. But what about other intersection? These curves doesn't intersect with this and this. And each one from this triple intersects with exactly 2 from this triple and this triple. And the same is here. So what do we have here? We have triangular prism. And for this triangular prism, we know it automorphs this group. It automorphs group will be S3 multiplied by the group of order 2. But to be the minimal, we should have orbits which consist of curves for that at least for each one curve in the orbit there should be a curve which intersects this curve. So at first we can see that there are no elements of order 4, and then from the elements of order 2 only one satisfies condition of minimality. This is something like reflection with respect to this plane. So if we change E1 to Q4, E2 to Q5, E3 to Q6, etc. So it corresponds to case Z10. Now we know something about this group, and we can start constructing our cubic surfaces. Well, if we will consider arbitrary cubic surfaces, that we can say nothing about it, since it's something difficult. There are not very easy to find the lines on this. But our method is the following. We don't want to consider arbitrary cubic surfaces. We consider special cubic surfaces. For example, we can consider cyclic cubic surface, which was defined in the previous talk. Here we will do it for Q equals to 3k plus 1. Well, what do we have? We have triple projection to projective plane. P2. And boundary divisor will be elliptic curve. This elliptic curve, it's given by the same equation as this. And so B have 9 inflection points. That means that preimages of these points on our cyclic cubic surface will be Eckert points. The proof is quite simple. Let P be what statement? I say that there are 9 Eckert points on X. At least 9, yes. They correspond to 9 inflection points. Well, let P be inflection point on B. And P0 be a point on X. Let us consider intersection of X and tangent space at this point. Then the multiplicity of this point in this intersection will be equal to 3. Since here we had inflection point. So, and since multiplicity is equal to 3, the only one possibilities for this section, hyperplane, is to be intersection of 3 lines at point P. So it's Eckert point. Well, now we want to prove a very good lemma. Lemma is following. If there is 3 conjugate points, inflection points on B, I will call it P.
What do you mean by conjugate here?
Conjugate, that it's they are permuted by the Galois group action. Yes, P, Q, and R. Not better notation. The better notation is P, gamma P, and gamma square P, when gamma is some element of the Galois group. And such that they are not lying on one line. Then type of the group acting on the wild group, the image of Galois group, I will call this group gamma. Then its type will be exactly C14. It will be group of order 9. How to prove it? Well, yes. Also, I forgot to say that this result is based on our with Sergei Rybakov paper. Well, so what we have in this situation? Consider 3 corresponding Eckert points on cubic surface. Let A, B, and C be 3 lines passing through one of these points. Then other lines will be gamma A, gamma B, and gamma C, and gamma square A, gamma square B, and gamma square C. Well, we know that there is only one group of order 9 in our wild group. So the order of group acting on this set of points should be divided by 3. And we can consider a subgroup of order 3 in this group. Let G be generator of this group. Well, moreover, we can assume that gamma is generator for simplicity of notation. What possibilities do we have? We have two possibilities. First possibility is that line A intersects with line gamma A. Yes? It's obvious that one line intersects not least at exactly one lines from each triple, since the class of some of these devices will be anti-canonical. Well, so first assumption, we assume that A intersects with gamma A, but then acting by gamma, we have that gamma A intersects with gamma square A, and also gamma square A intersect with gamma A. What does it mean? That means that A, gamma A, and gamma square A are three lines meeting each other. But three lines meeting each other. Where? Yes, thank you. So three lines meeting each other on the cubic surfaces form anticanonical class. They lie in one plane. But if these three lines lie in one plane, then we can consider section of our cubic surface by this plane. And that means that 3 points, the 3 Eckert points, lie on a line. And we have contradiction, since we say that the 3 points don't lie on a line. Well, so A and gamma A are just joint curves. But in this situation, A should intersect any other curve, for example, gamma B. Consider the curve gamma C. The curve gamma C cannot intersect with A, since A meets only one curve from this triple. It can't intersect with C, since therefore will be the first case. Then it intersects with a curve B. And the same for C. But now we have that gamma B intersects with gamma square C, and also gamma square C intersects with A. So in this case we have the same. We have that 3 minus 1 curves line in one hyperplane section. And that means that 3 corresponding inflection points line on a line. So we have contradiction in this situation. And the only possibility is for the group action. It's C14. In this situation, everything is clear. Well, so applying this lemma, we reduce construction of our cubic surface to construction elliptic curve with with a given property, with 3 conjugate inflection points not lying on a line. I think I don't have many times to do it, since I have only 10 minutes. But it can be done applying arithmetic on elliptic curves. And Doering theorem. Well, it was the case C14. What about 3 other cases? What?
Will you comment what the...
No, I don't want to comment. In the previous case, we see that if our cubic surface contains echoed points, that everything is good. Well, let's consider any cubic surface with any echoed point. It can be written down like, well, Q is odd here. The equation will be the following. Then point 0001 is echoed point. The plane Z equals to 0 contains 3 lines. And there is an involution action on this surface, geometric involution. What do we do with this involution? Let's consider other cubic surface. It will be X, and we consider a surface X prime. It's quite looks like this one, but we have a new coefficient U, and U is not square in FQ. So let's look on points here and here. If we have a point on our first surface, then there acts a Frobenius automorphism. Yes? It's just simple way, just get to the power of Q. But what do we have in this case? Now we have a point with such equation, and Frobenius automorphism acts on it almost in the same way, but it multiplies last coordinate by -1. So the difference between these two actions is multiplying the last coordinate by -1. But this multiplication is the same that our geometric automorphism. What does it mean? It means that for cubic surface given by such equation, we can twist the Galois action by the geometric action. So actually it can be not for only this cubic and not for only this action, but we can do the same construction for any action geometric, for any geometric action. So if we have geometrical group, then we can twist the generator of the Galois group by the action of geometric group. And this twist gives us many good results. So if for such a cubic surface we have the action of group C10, then there exists a cubic surface with action of group of type 3. It's group of order 3 which acts conjugate to permutation 1, 2, 3, 4, 5, 6. If we have such a cubic surface with action of group C11, then we can construct a cubic surface with action of type C12. So we can construct just one type of this cubic, and the second one will be given automatically. But if we use this construction for C13, then nothing changes. It maps to itself.